I want to thank Sean and Uriel for inviting me to speak here. And this is joint work with my students, Jai Devacharya, Rakendra Das, Ashkan Jafarpur, Sheng Junpan, and Ananda Suresh. Okay, so this talk is about the confluence of machine learning, computer science, and information theory. And we are looking at the very classical classification problem, goes way back, pattern recognition, pattern analysis. And about 10 to 15 years ago, people from computer science have started looking at the problem, and they took a different viewpoint. They said, let's not look at what happens in the case where the number of samples goes to infinity and see how the error goes down. Let's look at what happens with a finite sample size and see what happens there. So you have a large support, so you're not in the asymptotic regime, and see how many samples you need to classify. And what we're going to do today is add to the mix a competitive approach that we borrow mainly from information theory and techniques that we get from information theory. Okay, and the results that I'm describing appeared in last year's cohort, but the same technique applies to many other problems, and we are applying them right now, and I'm sure other things can be done as well. So in this talk, I'll describe the problem, the motivation, some of the concepts and examples. There will be no proofs, but there may be some calculations. So classification, and as we said, is so old, I'm attributing it to Adam and Eve. So you have two unknown distributions, P and Q. There are two kinds of apples. And you get a training sequence, one drawn according to P and the other one according to Q. And then you get another test sequence, Z, which is drawn according to one of them and you don't know which. And your goal is to decide whether Z was generated according to the same distribution as X, namely P, or the same distribution as Y, namely Q. It's very simple. Okay, so for example, and everything that we'll talk about today will be IID. So if you get these two training sequences, X and Y, so you can see that X has mostly ones and mostly zeros and few ones, and Y has mostly ones. Then you look at Z and say Z has more ones than zero. Most likely it's generated like Y, and therefore according to Q. Okay, very simple. All right, and we want to make this precise, so we'll define the error probability to be the maximum of the error when Z is generated according to P and when Z is generated according to Q. So we're being conservative. We're looking at the worst error, and we want to minimize this error. Okay. So what are applications? So for example, spam, you train on a bunch of spam emails and on a bunch of legitimate emails, and now comes a new email, and you want to say, is it spam or is it legitimate? Or topics, you want to classify a document into one of the many topics, so you train on sports documents, you train on politics documents, and then a new document comes in and you classify it into two or more possible distributions. Okay, or medical diagnostics, you see some people that are sick, some people that are symptoms of people that are sick, symptoms of people that are not sick, and a new patient comes in, you want to say, is the person sick or not? What kind of illness they suffer from, and so on. Okay, and basically all of machine learning can be done that way, and maybe someone would argue life can be done that way because we always learn from our experience, and based on our experience we want to deal with new situations. So as we said, almost all of machine learning is variation of this theme, like maybe you don't know something about the supervised, unsupervised interaction, you can ask for samples, but there are variations of this very simple thing. Okay. So all this is good, but we see that this is a very clean definition, and therefore we like it, but it's not quite as clean as information theory. Right? Because how many sequences do we have here? 3, right? We have X, Y, and Z, right? And in compression, how many do we have? 1, right? So we have in compression, we have 1, here we have 3. That's too big of a jump. So we want something that has two sequences, and that's closeness testing that I'll describe. Okay. So what is closeness testing? So this is a problem that was considered possibly not first by them, but at least the approach we'll look at was by them. It's by Batu, Fortno, Rubin, Fell-Smith, and White about 12 years ago. And this said it's the same thing. You have two unknown distributions P and Q, and you have two sequences X and Y that are distributed according to either P or Q, each of them according to P or Q. And your goal is to decide if the two sequences were generated by the same or by different distribution. Both of them by P, both of them by Q, or one by P and one by Q. Okay. So again, example, again, everything we'll do is IID. If you're given these two sequences, you're told they're generated IID, most likely you'll say generated by two different distributions. On the other hand, if you're given these two sequences, they have the same number of ones, think, yeah. So most likely you'll say they're generated by the same distributions, especially if you wait for long enough. Okay. Okay. So, and what is the error probability? So again, we're being cautious, so we're looking at the maximum of the probability when the two sequences are generated by P or by Q or P and Q or Q and P. So we're looking at all those possibilities, we're looking at the error that we make, and we're considering the worst possible error, so we're being very conservative.
Oh, I'm sorry, is this P sub R, is that meant to be PR?
Probability. Yeah.
Okay.
Yeah. Mm-hmm. Yeah. And what are some applications? You can think of authorship, so you get two documents, you ask whether they're written by the same person, or what we call banana ship. You can go to Whole Foods, you can go to your local grocery. There's a price difference, but after a while you want to say are those bananas coming from the same source or not. And the application that we care about is actually classification. Okay? So what I'm going to show is that closeness testing is actually the same problem as classification. Okay. Right. So I'll show you that closeness testing is a more difficult problem than classification, and if you can do closeness testing, you can do classification. Right. So we're assuming that you have a closeness test. So suppose P and Q have a closeness test that can determine if the two sequences generated by the same or by different distribution with error probability less than epsilon. So let's assume that we want to show we can do classification. Okay. So when we do the classification, we'll be given two training sequences, X according to P, Y according to Q, and we want to decide what Z was generated by. Okay. So we do something very simple. We just check X and Z and do a closeness test on X and Z. If the result is that they're generated by the same distribution, then we'll say that Z was generated by P. If the answer that the closeness test gives is that different, then we know that Z was generated according to Y, to Q, same as Y, and therefore our error probability in either case is less than epsilon. So if we can do closeness testing, we can also do classification. Okay? And we have the advantage that closeness testing has just two sequences, so it's a lot easier to describe. Okay? Now, so this is what I just said. If the answer was same, then we said Z was according to P. If the answer was different, for the closeness test, then we said Z was generated according to Q. Okay? So therefore, if we have a correct test, we have correct classification, and the classification error probability is less than epsilon. Okay? Right. So this shows this direction. The other, we are not going to use the other direction. We're going to use this direction, but the other direction is not much different from this one. Okay. Right. So from now, we're only going to consider closeness testing. Okay. So a word before we start. I want to say a word about the error. So suppose that with n samples, we can get an error which is strictly less than half, let's say 10%, but it wouldn't make a difference, was 40%, something which is strictly less than half. Okay? Suppose we can do it with n samples. Okay? Then what we can do is we can take these n samples and now repeat the test t times. So we just take t times as many samples. Okay? So we'll be using t times n samples. And then we take a majority of these t decisions. So for every one of those t blocks, we make a decision, same or different, and we take the majority. Okay. Now, so for example, if the decisions that we got were same, different, same, different, same, then we say the majority is the same. So we say these two sequences were generated by the same distribution. Okay. Now, what is the error that we get for this? This newer test takes more samples, it takes t times n instead of n. But what is the error? So we make an error only if the majority of the decisions are wrong. Now each decision, in this case, if it's 10%, is wrong with probability at most 10%. So we're flipping a coin, each one's probability of getting the wrong answer is 10%. What's the probability that more than half of them will be wrong? This probability is going to go down exponentially. So its decision log probability 10%, so the probability of error is going to go like exponential with t. Okay? And if now someone gives us any error epsilon that we want, then we want this to be less than epsilon, so we want t to be 1 over c times log of 1 over epsilon. Okay? And so the number of samples that we need is the original number n times t, so it's n times 1 over c times log of 1 over epsilon. So as we can see, the dependence on epsilon is very moderate. It's like log of 1 over epsilon. So if someone gives us like epsilon, which is, I don't know, 1%, then you multiply it by some small number. And we're not going to care about small constant. So for us, so is that clear? So very quickly, once we get some error like 10%, it goes down exponentially. So we're not going to care about what the error is. So for now, we're going to ignore epsilon and assume 10% error, so we can get rid of at least one parameter, so we don't need to worry about that. Okay, right. And we're going to let n. So if we have a test t and we have these two distributions p and q, we let nt of pq be the number of samples that this test t needs to test p and q with 10% error. So we don't have exception. It's okay? Okay. So that's one observation about the errors. And another second observation is about label invariance. So we're going to learn, as we always do in machine learning, we learn everything from the data. Okay? So all labels are equally meaningful. There's no distinction between them. So the test should be unchanged under one-to-one relabeling. What do we mean for that? So for example, if I give you these two sequences, A, B, B, C, and B, B, C, D, then maybe you test, remember it's IID, your test might say that these two are generated by the same distribution because you see the same number of C's and B's and so on. Maybe it will say the same. If it said whatever the answer it gave here, it should also be the answer here when we just change every A to alpha, every B to beta, and every C to gamma and so on. So if we change, the answer should obviously be the same. Right? It cannot be that the test will tell you these are the same and these are different. That doesn't make sense. Notice that when we do the relabeling, we need to be consistent between sequences. So we cannot change only the second. Here I kept the first sequence the same, but I changed the second sequence. Then we don't claim anything about the test. When you do the relabeling, it has to be for everything. Okay? So we're just saying this should be the same. Here we don't know. Okay? So this, it makes sense that we'll consider only such algorithms. In fact, that's what people do, and they call them canonical tests, canonical algorithms. Okay? And all they mean is that the observation names or the language that you use should not matter. Okay? And it seems obvious that that's what the test should be, right? Obvious to everyone? Okay, we'll come back to that. All right, okay. So what results have people gotten? Okay, so this is again the paper by Bato et al. So they said, suppose that your distribution is of an alphabet of size at most k, and the L1 distance between the two distributions is at least some delta. So these are parameters someone gives you. Someone gives you k alphabet the size is most 1,000, and the L1 distance is at most at least 0.01, let's say. Okay. Then they came up with a test t such that for all such distributions, all P and Q that satisfy this, okay, these conditions, the number of samples that this single test needs is at most k to the 2/3 times log k. And then there's some constant dependence on delta, which okay? So we're going to concentrate on the exponent here, 2/3, okay? And they also show that this exponent is tight in the sense they show that you can find two distribution PQ such that no matter which test you come up with, even if you design a test specifically for this P and Q. Notice this test that they came up with holds for any P and Q, but even if you design a specific test for this P and Q, then it will need at least k to the 2/3, just the same as the upper bound. So in some sense it's tight, okay? And so these results are nice in the sense that, first of all, are pretty, and I think what they like the most is that it's sublinear in k. So the number of samples that you need does not go linearly in the alphabet size.
Which is what you'd expect from a lot of statistics, that's very
right.
universal statistics.
Cool. Yeah. So if people talk about big data, you have a lot of, doing something on English, the alphabet size is very large, and then you don't need to go all the way to the alphabet size. And obviously people like that they got the right power, okay? And there have been many follow-ups. I listed a few of them here. Okay, so this is on the good side. On the not so good size. The algorithm requires knowledge of an upper bound on the support size. So someone needs to tell you the alphabet size is most 1,000, and they need to tell you that the L1 distance is at least 0.01, for example. So they need the upper bound support size, lower bound on the distance to design the algorithm. And in general, these bounds may not exist, so the support size could be infinite. And it could be, look at distributions, infinite support, for example. And even if they exist, you may not know them. So like who tells you, if I'm looking at two people writing a book, who tells me what is the lower bound on the distance, L1 distance between distributions and so on. So either one of those may not happen. Either they don't exist or may not be known, okay?
Question.
Yes.
The test depend on the data.
Correct.
The test also depends
Correct.
on
Correct.
not just the performance.
Correct.
Let's say I overestimate and say the alphabet size is really big, my test will work, but
It will require more samples.
Oh, requires.
Yeah, it will require this k to the 2/3, this new k. And
So not only their algorithm is might work badly, but this particular.
correct,
the
correct.
worst.
That's right. The behavior, that's another thing that will come to. The behavior, not just a question of correct or not correct, but also the complexity of the algorithm will depend on the alphabet size. The performance will depend on the alphabet size. We also don't like that. So second thing is why L1. So we'll see L1 is not necessarily the right thing to look at. And subsequently, indeed, people have looked at other distances. But again, we don't think these are the right distances to look at. And another thing we don't like is that it's a worst case. So that what they say is that for all these collection of classes, they come up with an algorithm that requires these many samples. And there is a pair in this collection which requires that much. It's kind of a worst case analysis. But there may be other pairs that require less. And that's not captured by this. Okay. And so we'll talk about the L1 in the next slide, and we'll talk about the worst case in the slide after that. Okay. So first we want to show that the support size and the L1 distance are not necessarily indicative of how difficult it is to classify or to do closeness testing in this case. All right. So what we'll do is we'll show two distribution pairs that have the same support size, it will be 2, and the same L1 distance, which will be delta, but yet they require different support sizes, different sample sizes. Okay. Okay. So recall that we're only looking at 10% error. Okay. So the first pair is going to be Bernoulli 0 and Bernoulli delta. So alphabet size 2, L1 distance delta or 2 delta. And we're going to show a very simple test that requires at most 3 over delta samples to get to 10% error. Okay. So what would be a very natural test? So you're getting n samples from 2 sequences, each of them n samples. And you want to know if they're generated by the same distribution, namely Bernoulli 0 or Bernoulli delta, both of them, or one Bernoulli 0 and one Bernoulli delta. What is the most obvious test you would do? So you look at the ones in the sequence, right? Delta is the probability of 1. If both sequences have ones in them, or both sequences don't have 1 in them, then you'll say generated by the same distribution, right? If both of them both of them are all 0, then you say both of them are Bernoulli 0. If both of them have 1, then you know for sure that both of them are Bernoulli delta. Then you'll say the same. And if exactly one sequence has 1s and the other sequence does not have 1s, then you'll say different. Very clear, right? What is the error probability of this test? So first of all, observe that if Bernoulli 0 will always give you 0s, and Bernoulli delta, the probability that will give you this many 0s is going to be 1 minus delta to the 3 over delta, which is less than 1 over e cubed. Very conveniently, 1 over e cubed is 20 and a little bit.
The Q of the string.
Correct. So Q is one of your distributions, Bernoulli delta. And what is the probability that this distribution Bernoulli delta will give you a string of 3 over delta 0s? It's 1 minus delta to the 3 over delta. Okay. So it's just slightly less than 1 over 20. Okay. So what is our error? If both sequences were generated by P, then for sure both of them will be 0 and you will not make any mistake. So the error probability then is 0. If one of them was generated by P and the other one was generated by Q, the only way you'll get a mistake is if Q gave you the all 0 sequence. Okay, and that's this probability that we calculated here. So that's less than 5%. And if both of them are generated by Q, then you make a mistake if one of them gave you is all zeros or the other one gave you all zeros, and maybe slightly less than that, but that's an upper bound, so it's less than 10%. So we're good. So what that shows is So what that shows is that in this case it's sufficient to look at 3 over delta samples, okay, to get 10% error. Now let's look at another pair of distribution, P prime and Q prime. They're over the same alphabet of size 2. They're both Bernoulli. They're also Bernoulli, and the L1 distance between them is again 2 delta. Okay, so same as before. So one of them is half minus delta over 2, and the other one is half plus delta over 2. And let's see how many samples we need now. So so clearly the only thing you can look at is the number of ones that you observe. And what you need in order to be able to distinguish between them, they need to be separated by some standard deviations. So it needs to be like there are a certain number of standard deviation apart, so that one will fall on this side, one will go on this side, and one will threshold. If that is not separated by standard deviation, then you'll be making mistakes. Right? Okay, so if we take n samples, then the standard deviation, both of them are roughly a half. I'm thinking of delta as being small, so you have Bernoulli half, the standard deviation is square root of n over 2. And the distance between them is n over 2 minus n delta over 2, and n over 2, that's the expected here, and n over 2 plus n delta over 2. So the distance between them is n delta. Okay? And you want it to be bigger than some number, whatever this number is, of standard deviations. Okay? So therefore you want n to be bigger than 1 over delta square. So what we see is that any test that you come for these two distributions will require a number of samples, which is at least 1 over delta square. Okay. So this shows you that they have the same support size 2, the same L1 distance, which is 2 delta, but requires the square of the number of samples. Okay. So the L1 distance is not the right measure, so the support size is not the right measure. The distance, L1 distance, and other distances are not the right measure, and so this is not what we want to look at. Okay. Okay, so in contrast, what we want to do is a little more information theoretic, and I want to contrast it to our worst case analysis. So we have a sequence of length n distributed according to, so in data compression, we have a sequence of length n distributed according to some probability p, and again, we're going to assume now IID, which we want to compress, right? And if p is known, we know that we need the entropy of p bits per sample, and you can achieve it in different ways, okay? And so the question is, what is the entropy? So if P is uniform over K elements, then the entropy is log K. On the other hand, if P is 1/2, 1/4, and so on, again on K elements, now the entropy is less than 2. Okay? So if we had a worst case results, we would say that for every P, we need at most log K, because this is log K, and there exists a distribution that requires that much. That would be the equivalent log worst case result. It says any distribution over K symbols, you need at most log K, because the entropy is at most log K. And conversely, there is a distribution for which you need so much. That's the analog of the type of results that people typically get for these problems. Okay? And there exists distribution. And what we want to do here is we want to get the best possible, not just for the worst distribution in class, but for every distribution. So the equivalent in the other problem would be for every 2 distribution P and Q, we want to get the best that you can for those 2 distributions, not aim for the worst pair in the class. Okay, so that's the competitive version that we're looking for. Okay. Now, in this case, for simplicity, we assume that P is known. If P is not known, then the universal compression results, and they show that you need an entropy of P plus order of log n over n. And those are similar to online prediction with experts and other losses and so on. So what we want to do is, what all these do is they approach this the best possible for this distribution and for every P. And what do we mean by best? It's something that's competitive with someone who is more informed, like in this case, someone who knows the distribution. Okay? So this is what we want to do. We want to get competitive results when what you get when P is known in advance. Okay? So this is our goal. Okay, so we want to generalize these results from compression and from online learning and so on to classification and other learning tests. Right. Okay. So the goal is to approach the best performance for every P and Q. And by best we mean when P and Q is known in advance. And so T is going to be some closeness test, and NT of PQ is the number of samples you need for some given error, which in our case is 10%. And N star of PQ is the minimum number of samples that the best algorithm would need. So you take all algorithms and you find the one that requires the least number of samples to get to epsilon error. You could see from the previous examples that we gave that the tests may depend on P and Q. So in general, if you know P and Q, you will design a different test. And that's N star of PQ is the smallest number of samples that are needed for P and Q. And in general, to achieve this number, you need to know P and Q in advance. You cannot just use one algorithm and do it for all PQ. You need to know PQ, design something specific to get to N star of P and Q. Okay. So what we want is a single closeness test T, does not depend on P and Q, and this T has this property that for all P and Q, the number of samples that it will need to get to 10% error is going to be some function of N star. What do we mean by some function? For example, it could be, this will be really good if you get at most 3 times and the N star, or maybe the square or so. Okay? Okay. So, and the results that we want and that we'll get are non-asymptotic. So we're not looking at the case of what happens to the limit. We're looking at any. This holds for any P and Q. There's nothing hidden here. There'll be no asymptotics. For any P and Q, you want it to be that function. We will not get 3, I can tell you already, but whatever the answer we want is going to be, there will not be any asymptotics. It may depend on epsilon, but the dependence on epsilon is, as we said before, is very mild. So if you want to multiply the log of 1 over epsilon, so it's a very small dependence. So we're just doing it for 10%. The idea behind this thing is that you don't want to look at error exponent, because once you don't care if your error is 10 to the minus 10 or 10 to the minus 20, because by the time you get to these things, something else will go wrong. So you want to get to error which is, let's say, 5% error in you do classification, or 1%. So we're not looking at what happens for very, very small epsilon, but you could. Okay, so so what if we can do it? What would be the advantages? So we approach the performance of an oracle, of someone that knows P and Q, and therefore it's the best that is humanly possible. And after all, this is what we strive to achieve, right? The best that anyone without super knowledge would know. Okay. And another advantage is that we don't look at distances. We just look at the error, and that's our measure. So it's information theoretic in that respect. We want to achieve error, we look at the error. We don't look at L1 distance and so on. Okay, so we think it's beautiful, but that's it's in the eye of the beholder. So, all right, okay. So one question that you could ask is, how do you use these results? Because in general, you will not know what N star is, right? You're given 2 samples, you don't know what P and Q are, so you don't know what N star. How do you know what N should be? Even let's say you knew this. Let's say we proved this formula. Let's say, okay. How would you know if you don't know N star? And indeed you don't know. But the way you'd use this result is, someone gives you a certain number of samples. Let's say 1,000 samples. You'll use the algorithm for this number of samples, and you say that the error that you get is less than the error that the other person will get with F inverse. Okay? So for example, here it would mean that the error that you get is at most the error that the best person would get with 1,000 divided by 3, or square root of 1,000 samples. That's how you'd use this result. Okay. Right? Okay. So first question, is this possible? Okay. So okay. So can you approach this? Can we get something which is competitive with a person who knew the distribution? Okay. So let n is the number of samples, be arbitrarily large. Okay. And we want a result that does not depend on k. The result should hold for any P and Q, so any alphabet size. Okay. So imagine that you have a distribution over alphabet size k, which is the square, much bigger than the square of n. Okay. And let S be some arbitrary subset of this. So you have alphabet of size k, and let S be a distribution of an arbitrary subset of size k over 2. Okay. And let P be uniform over S. My goal here is to show you that actually maybe you cannot be competitive. That's the question, right? So I'm giving you a potential example where you cannot be competitive. So I'm saying, let's say that we're allowed 1,000 samples, 1,000 being a large number. Let's take alphabet of size 1,000 square, 1,000,000, and let's choose 2 distributions. One of them is going to be some arbitrary subset of 1 up to 1,000,000 of size 500,000. Okay, that's S. And P is uniform of this set. and Q is going to be uniform of the complement. Okay, very clear? Okay. So if we knew P and Q, how many samples would you need to say, I give you a sample from P, or I give you two samples, one from either P and Q, the other one from either P and Q. How many such samples do you need to say if they come from the same distribution? Just one, because?
So you can check whether it comes from
Right.
both of them come from the same alphabet.
Right, because you can, if you know P and Q, we're trying to compete with the person who knows P and Q. The person knows P and Q, that means they know this set. They know this set, okay? So for example, so if X and Y come from the same set, or they come from the complement, then that person who knows the set will say the same, and otherwise they say different. For example, suppose the set is 1, 3, 6, and so on. That's S, and S complement is just whatever is left, 2, 4, 5, and so on. If we're given X is 3 and Y is 9, then they say they come from the same distribution, the same. And if they're given 3 and 5, because they know these two sets, they'll say different. Okay? So a person, so N star for these sets, this is not working too well. For these two distributions P and Q, N star is 1. Okay? On the other hand, if you don't know the two distribution P and Q in advance, you need at least n samples. Why? Because by the birthday paradox, if you choose less than n, then every element of X and Y will appear once. Okay, so if we take less than n samples, then because the alphabet size is n squared, then we're getting less than square root of the samples from X and from Y. Okay, then every element will appear in X and Y will be seen once, whether it's the same or whether it's different, and so we'll not be able to tell it all. Okay. So this shows, so there's no way to tell if they're the same or different distributions. So this shows that NT of PQ must be arbitrarily higher than N star of PQ. Everyone agrees? Okay, so this shows us that so this shows us that you cannot do competitively, right? Because we showed an example where if you knew the two distributions, we need one sample. And if you don't know the distribution, we need an arbitrarily, we can come with, if you give me 1 in a trillion, I'll come up with an example where this is 1 and this n is a trillion. So there's no relation between them. But not necessarily. So what are we missing? We're missing the obvious. What was the obvious? The obvious was that the algorithm needs to be label invariant. Because here, the person knows P and Q knows too much. They actually know the labels of the two sets. They don't just know the distribution, they know actually what the values are, and the test actually depends on whether if I change this now, if I change this from 3 and 9, if I change 9 to 4, then the answer will change. So the answer is not label invariant. So we're competing here with something that is too strong. Okay, we only want to compare it with label invariant distributions. Okay? So this test is not label invariant, and so there's still hope. Okay, and so what we want to do is compete with a weaker oracle. Okay, and the logic that we would use is that we're not trying to compete with someone who has superhuman powers. We're just trying to compete with other companies, people employed by humans, and so on. So it doesn't matter if we beat like Superman or Superwoman or Catwoman, if we beat anyone who has powers that we don't possess, then we're doing as well as any other person. So all oracles for us are the same. So we just want to compete with a slightly weaker oracle. Okay. So all oracles for us will be equivalent. If you can get close to 1, that means you can get close to the best you can do. All right. Okay.
Can I ask a
Of course.
I didn't understand the notion of arbitrarily higher. For example, square is arbitrarily higher as well.
No.
In what sense do you mean?
Okay, cool. Okay, so remember we're trying to come up with an algorithm T such that the number of samples that we'll need is at most the square of the best, for example. Okay, some function of the best, let's say square, we'll actually do better than that. So, but here if you give me, this shows that you can come up, and this has to hold for any distribution. We're not looking for asymptotic results, we're looking for very clean results. Says here's an algorithm such that nt is less than n star square, for example. But here n star square, n star is 1. So any function that you give me, this could be 1, this could be a trillion. So I can come up with a distribution for which you'll need more. And we're trying to avoid that. We're trying to very clean results. It says that this algorithm is always at most a square.
To demonstrate this point, we really needed one where n star was 1.
If you want, but the point is, even if n star was not 1, let's say n star was 10, we could come up with something that will require a million, a billion, a trillion, and so on. So here this is the worst. We're coming to something where n star is 1, but any number that you give me, you cannot compete. And the reason is because you're trying to compete with a very, very strong oracle. The person who knows the distribution, it knows a lot. So we're just going to say we compete with someone who knows more than they should, but not that much. So we'll give them some information about the distribution, but not all the information about the distribution. Okay, so what we want to do is we want to look at the hypothesis testing framework and show that traditional techniques fail for this problem, and then talk about what we call profiles, and then some examples and results. Okay, so hypothesis testing, human testing, I don't know, legal? Maybe. It's a tough crowd here too. Okay, so here now we have two known distributions P and Q, unlike our case where they were unknown. So we have two known distributions P and Q. And the two hypotheses are that X is generated according to P or according to Q. And the optimal test is clearly if P of X is bigger than Q of X, then it's X is generated according to P, and otherwise Q is bigger than Q of X bigger than P of X, X is generated according to Q. Okay? The motivation would be like if you'd say that you have equiprobable classes, or the generated according to P and Q probability half, and then this will minimize the error probability if you use this criterion. What we want to think of is that this criterion just classifies to the distribution that better explains the data. This will be what we're going to keep with. Okay, so we're saying if P of X is bigger than Q of X, that means that P better explains the data. If Q is bigger than P, then Q better explains the data. That's what will remain constant for us. Okay, all right. So equivalent to that is the likelihood ratio test. Divide P by Q. If P of X and Q is bigger than 1, it's a P. Otherwise, it's a Q. Okay. Okay. So this is if you have just two hypotheses. Sometimes you don't know the hypothesis, but you have classes of hypotheses. You have two distribution collections, P and Q. And one hypothesis that X belongs to P, which is a distribution in script P, or X belongs to Q in script Q. And then the standard way to do that is to look at the maximum likelihood probability of X is the highest probability that any distribution P assigns to X. And then Q maximum likelihood of X, which is the highest probability that Q assigns to X. Okay, and use the generalized likelihood ratio test to look at P maximum likelihood of X divided by Q maximum likelihood of X. If this is bigger than some threshold T, then you say it's P, and otherwise you say it's Q. And again, it's the same reason where T is some threshold. And this can be shown to be asymptotically optimal as the number of samples goes to infinity. But remember, our results, we don't want it to be asymptotic, so this will fail, as we're going to see. Okay, so again, the reason is we're trying to see which collection better explains the data. Right? That's the, okay. So what do hypothesis testing have to do with closeness testing? So in our case, we have two collections. P1 is the collection of that they come from the same distribution, PP. And P2 is that they come from two distributions, which for a second, let's say they could be the same or different. Okay, so this is first hypothesis come from a single distribution, and two that come from some P and Q could be arbitrary. Okay, right. So the GLOT would say, let's look at the highest probability, maximum P of P1 of probability of X and Y divided by the maximum of P2 of P of X and Y, and compare it to some threshold. Okay, but in this case, you probably observed, P1 is a subset of P2, so this maximization will always be larger. The denominator will always be larger, so this this likelihood ratio will always be less than or equal to 1. So that means just that the threshold will be some number less than 1. Okay, so and so if x and y are explained by the same distribution, if there's one distribution that explains both x and y, then we expect this to be roughly the numerator and denominator to be roughly the same, and the ratio to be roughly 1. So then we'll say same. On the other hand, if they're explained by two different distributions, then the ratio will be, this will be much larger, so the ratio will be much smaller than 1, and then we'll say they're different. Okay? Okay. Okay, so what I want to do now, in order to show you the results, I need to do some calculations as I told you. So do you want to do that, or you want to skip and go to the results? It actually, there's one more surprise coming up, so I think, but in order to understand that surprise, I think we need to go over the calculations, so go with me. They're not difficult, they're easy actually. Okay. So so I want to do these calculations specifically for the example that we're looking at, sequences, okay? So what is the maximum of a P2 is the collection of that says that x and y generated according to two different distribution. What is the highest probability of x and y? In this case, it's the maximum of all p and q of p of x times q of y, because we generate x and y independently, just becomes the product. And we can maximize for p and maximize for q. Okay? So it's just p maximum likelihood of x times p maximum likelihood of y. Okay? On the other hand, if we say that they come from the same distribution, then it's the maximum of a single p of p of x times p of y, because we're looking at a single distribution. And again, generated independently, it's the product. So then p of x times p of y is just the probability of the concatenation. And we're just looking at, so it's just the highest probability of the concatenation. So this is what we're doing. The ratio is very simple. It becomes the highest probability of the concatenation. That's when they come from the same distribution, that's P1, divided by the product of the maximum likelihood. If this ratio is close to 1, then these two sequences are equally explained by one distribution. If this ratio is much less than 1, then two different distributions explain it much better. Okay. Right, so let's see what P maximum likelihood of x is, and remember we're looking at IID. So which distribution maximizes the probability of what we observe is just the empirical distribution. So if you're looking at the sequence 1, 0, 1, 0, 1, which distribution will maximize it? It's distribution maximizes alpha cubed times alpha bar square, which is 3/5 to the cube and so on. So which is 2 to the minus n times the entropy of 3/5 and so on. And similarly, if you have any other sequence, it's 2 to the minus n times the entropy of the p. P is the fraction of ones. Okay. Right. So let's see what happens when the sample size is larger than the alphabet size. So we have a fixed alphabet, the sample size is large. Okay. Then, if the two distributions are generated, if the two sequences are generated by different distributions, for example, if x is distributed Bernoulli 0 and y is Bernoulli 1, then x is going to be 0 n times, y is going to be 1 n times, and the concatenation is 0 to the n, 1 to the n. And now we need to look at the ratio of the maximum likelihood of this concatenation divided by the maximum likelihood of the product. Okay? So the maximum likelihood of the top is going to be 1/2 to the n, and for the 0 to the n is 1 n times 1. Right? So here I have a sequence which has n zeros and n ones. What is the highest probability we can get is 1/2 to the 2n. And I divide by the highest probability of 0 times the highest probability of 1. It's this value, okay? And which is the same as 2 to the minus entropy, okay? Which is 1/2 to the n. So the point line, the bottom line is that this ratio is much smaller than 1. Why? Because you can explain 0 to the n and 1 to the n separately much better than you can explain them together. That's what this says. Okay. Similarly, if you have Bernoulli P and Bernoulli Q, then this is what you'll get, and I just don't want to bore you too much. You get the ratio of the entropy. So so they're generated according to Bernoulli P and Bernoulli Q. If you try to explain them together, then you'll get 2 to the minus entropy of P plus Q over 2. And if you try separately, you'll get the entropy of P plus the entropy of Q. And by the convexity, of entropy, this will go down exponentially. Okay, so that's the only thing we want to say. Okay. On the other hand, so if they're separated, if they're generated by two different distributions, then this ratio will go down exponentially. On the other hand, if they're generated by the same distribution, so let's say both generated Bernoulli R, then both x and y will have roughly r fraction r of 1s, okay? And so will the concatenation. And so when you look at the ratio, you'll get roughly 1. Because you'll get 2 to the minus n h of r and 2 to the minus n h of r, and here 2 to the minus 2 n h of r, so this 2 will cancel. So if they're generated by the same distribution, this actually there'll be a polynomial, because you won't get exactly this thing. It'll go down like 1 over polynomial. If generated differently, they go down exponentially. So we can set the threshold that's any reasonable exponent, and it will work. Okay. So, and that's because they're equally explained by single distributions. Okay. On the other hand, let's see what happens. So this is when the alphabet is fixed and the sample size goes to infinity. We can use the maximum likelihood ratio test, the GLRT, the generalized likelihood ratio test. Sorry. Okay, so on the other hand, let's see what happens when the number of samples is not so large, and let's say smaller than the alphabet size. And let's see if we can use that. Okay. So this example is appeared in a paper that we wrote, but it's actually modified from another example that was done by Wagner and Viswanath and 2 of their students a year before. This is simpler. So take alphabet size, which is the square of the number of samples, bigger than the square of the number of samples. Okay. So we have 2 distributions. P is just a singleton. So one element A has probability 1, and everything else has probability 0. And Q has probability half for A, and then the remaining half is probability 1 over 2 times K minus 1 for the remaining K minus 1 symbol. Okay? So very simple distribution. 1 always gives us A, 1 gives us A with probability half, and uniform over the rest of the symbol. Okay? So let's see what happens when we generate the 2 distribution the 2 sequences according to, one according to P and one according to Q. Okay? All right. So X we generate according to P, we'll just get A to the n, there's no question, right? P is just always gives us A, so we generate n samples, we get A repeated n samples. Q, half the time we're going to get A, so A will repeat roughly n over 2 times, and half the time we'll get one of the remaining symbols, but because K is bigger than n squared, again, birthday paradox, all of them will be different. Okay, so this is what we expect to see. We expect here to see A all the time, here we expect A to see half the time, and the rest are different. Okay, and so the concatenation is A appears 1.5n, and the rest are different. I'm about to run over the second slide changer. All right. Okay. So now we look at the ratio of the probability when they're generated according to the same distribution and the product according to different distributions. Okay. So we're looking at maximum likelihood. In the concatenation is A appeared 1.5 times, and the rest were different. And the product is A to the n and this one. Okay. So what is the probability? So for this one we have both of them we have 2n symbols, and 3/4 are A, so it's 3/4 raised to the 3 over 2n times 1 over 2n raised to the n over 2. And in the denominator, A to the n is 1, this is 1, and this one is half to the n over 2, and 1 over n to the n over 2. Okay? Because they're n symbols that we see here. So when here the n's cancel, the half cancel, you're just left with this 3/4 to the 3 over 2. So it's 0.65 to the n. So it goes down exponentially as you expect, right? Because we expect they were generated according to 2 different distributions. We expect the probability to go down exponentially, the ratio, right? Because we expect the 2 different products to explain it much better, to go aside of that. Now let's look at what happens when they're generated according to the same distribution. Now we expect this and this to give us roughly the same number, because there's no reason for you to choose 2 different distributions in the denominator. You should be choosing the same distribution. So we expect this ratio to be roughly 1. Okay, so let's see. So let's choose X and Y to be generated according to Q. Okay. So X, just like before, we expected to see A to the n over 2 times B, C, and so on up to G. Okay. And Y, again, n over 2 A's, and the remaining should be different because the alphabet is so large. Okay. So the concatenation is A appearing n times, concatenate, and then you have another n symbols each appearing once. Okay. Now let's look at the ratio. So it's the ratio of the highest probability of this sequence, the concatenation, divided by the product of the highest probabilities. Okay. So for the concatenation, we have half a, so it's 1/2, and this appears n time, raised to the n. And then we have 2n symbols remaining, 1/2n, raised to the n. And the denominator, each one is half to the n over 2 times half to the n over 2, we square it. Okay? And when you multiply, you get 0.5 to the n. So actually it's smaller. So not only is there no, you cannot put the threshold between them, but what you expected to be higher is actually smaller. You can better explain this than you can explain that one. So that shows that no threshold will work. This technique does not work. Okay. Right. And the reason you can see is because you're trying to explain here more symbols. You get another factor of 2 here, and that's because this is what kills you, because you have 2n symbols, so you get this factor of 2, and that's what gives you the 0.5 to the n. If it wasn't there, you get 1, which is what you expect. So if you're looking for results that apply not asymptotically, but apply for anything, you cannot use likelihood ratio test. Okay, so this is what we just said. Okay, so so the way we get around this is by moving from sequences to types and then to profiles. So a sequence is just what we observe, for example, heads, tails, and so on, or the word Boston, let's say IID. Okay, and the type here says that H appeared. This one, maybe this. Okay. Yeah. Thanks. And the type says, thank you, that H appeared twice and T appeared 4 times. Okay, so and the profile, so the type just says number of times, so the multiplicity is the number of times that each symbol appeared, and then the type is the set of elements and the multiplicities. Okay, and the profile, it's just the multiset of multiplicities, so here it will just be 4 and 2. Okay, or Boston, we have B appearing once, N appearing, this is the type, N appeared once, O appeared twice, and so on. What is the profile? We just eliminate the labels, and we just say there's 1 symbol appeared twice, and 4 symbols that appeared once. And that's the profile. Okay. And we've worked before on profiles, and we showed that that you can use profiles for estimating distributions, and you can apply it. We also applied it empirically to classification, and what we do now is apply it to classification closeness testing, not empirically, but to get theoretical results. Okay, and for that we need to extend the profiles to 2 distributions. So so here we need to classify say whether 2 sequences come from the same or different distributions. So we'll look at pairs of sequences, for example, H, this sequence and this sequence, and so on. So here H appeared twice in the first sequence and once in the second sequence, and T appeared 3 times here and 4 times here. So this is the type, and the profile is we just write 2, 1 and 3, 4. That means there's 1 symbol that appeared 3 on the left and 4 times on the right. There's 1 symbol that appeared twice on the left and once on the right. We don't care which one. Okay. Similarly, for madam and man, there'll be A that appeared twice on the left and once on the right, and so on. And so the profile is just a collection saying that there's 1 element. Actually, there'll be 2 elements that appear twice on the left and 1 on the right. That's A and M, and so on. That's the joint profile. Okay. So we're looking at the multiset of joint multiplicities, and this is sufficient statistic for closeness testing. You can see that if I give you this information, that's as much information as you have here. All you care is there's 1 element that appeared 3 times on the left, 4 times on the right, the 1 element appeared twice, you don't care about the labels. Okay. Right. So what we do is we do GLRT on joint profiles. Okay. And so instead of looking at the sequences, we just do it on the profile. We look at the highest probability of the profile, and then we do the GLRT. So because we don't have time, then if you do the same thing on the sequences that we got, you'll see that you get what you'd expect. So so you see here that this GLRT works. All right. Okay. So what are the results that we get? So
that it goes down polynomially.
Actually, that's not the issue that we use. That what we use, I mean, it probably does, but we don't use that fact because we just want to compare ourselves to the best error that anyone can get. So we just need to look at the ratio. and the ratio will go down sub-exponentially. So the ratio between. Okay. So let n star be the smallest number of samples that you need to do closeness test for P and Q, and to achieve it requires prior knowledge of P and Q, and this is by a canonical algorithm. So what we have is a single test T, such that for every P and Q it requires at most some constant times the best you can do, raised to the 3/2 to the 1.5. Okay. And this holds for any k, any distance, the distance won't matter even, any P and Q. So any P and Q over anything you give us, this will always be the case. And we also show the converse, like somewhat converse, that for every test that you come up with, there will be two distribution P and Q, such that the number of samples you need will be at least this n star raised to the 7/6. So there's a gap here between 7/6 and 3/2 that we don't know. Okay. And similar, this will translate to results for classification. Okay. So, so there's some possible explanation that goes through the number of types and the number of profiles. The number of profiles does not depend on the alphabet size. That's why we can get results that apply for anything. Okay. And joint profiles and so on. So independent of K, independent of the distribution. And conclusions, talked about classification, closeness testing. We said they're roughly the same problem. And we said that the results that people have gotten is that they have shown that the sample size is sublinear in the support size, but the results required knowing the L1 distance, and they're geared towards the worst in the class. And what we showed is competitive in the universal compression sense approach, where n star is the smallest number of number of samples needed for closeness tests by an algorithm that knows the distribution. And using profiles at maximum likelihood, we can get a single test that requires at most this n star raised to the 1.5. Okay, and then we also show that you can get below n to the 1.5, but no better than n to the 7/6. Okay. And so this is a single test that approaches the best for all distributions. Okay, and note that one could hope for better competitiveness, but observe that this is compared to idealized tests that nobody can achieve. So it's not that what we're comparing is something that nobody can achieve. Okay. And so maybe stop there. Right.
So let's say there are 1 million terms at most, okay?
Right.
3 million terms at most. So we have something called a term document frequency. So 3 million words, 3 million terms, what's the frequency for each document?
Right.
So we have this kind of document, this vector. So we have 3,000 documents, we're going to have 3,000 rows.
Correct.
And 3 million columns.
Correct. Right.
To the terms. So given this matrix, so how can I apply your technique to classification?
So basically you'd use the data. What you described now is the profile. You're looking at the rows. If you just ignore the labels, like the names, then you have, let's say, 3 rows, or what we talked about here is 2 rows. For each word, you say how many times it appeared in this document, how many times it appeared in that document. That's your profile. Okay. And then you can do that if you're given 2. We said the way I described it here was for closeness testing, right? So if you give me 2 documents, then I can tell you if they were generated by the same or different distribution. That's what we describe now. Okay, I didn't describe the algorithm, but that's what the algorithm does. So your problem is classification. So you need to go back to the beginning of this thing and say, if you now have the training sequence X and Y, and then comes the new document Z, let's say, that you want to classify. Then you compare Z to X, and if they're generated by the same distribution, if their answer is the same, then you say z is similar to x. Otherwise, you say z is similar to y. The catch is that everything that we have talked about so far is for IID distributions. Now, when you say that you're looking just at the word frequencies, essentially you're assuming that because you're not looking at the relation between which word came after which other one. I say how many words, how many times each word appeared. So you're making the same approximation. And if you're happy with that, just ignoring the relation between consecutive words, not looking at bigrams or trigrams, if you're happy with it, which sounds like you might be because you're just looking at word counts, then you can just use that. And we have an algorithm, of course.
Can I ask a really naive question? So, if you were to give me two data sets like you did, particularly given assuming they're IID and presuming they're coming from the finite alphabet, how I would test...
Finiteness is not important because our result has no dependence on the alphabet itself.
Okay, so the way I was listening to you talking about finite alphabet,
Right, okay, yeah.
is I would take the two things and concatenate them and do the runs test. Right, it's a beautiful thing from the 1940s.
Which test?
The runs test.
Okay.
It looks for... so if the things... It's really nice because it's a joint test for whether they're independent as well as whether they're identically distributed. What it looks for is transitions in runs for sequences of zeros followed by sequences of ones. You can't tell how many transitions there are. You do it on a finite alphabet. And it's kind of like a single test on an entire string. So your example where you have n over 2 zeros and n over 2 ones will immediately reject.
Correct.
And I was just... What I couldn't get from this is like, so you're telling us kind of explicitly some methodology that will work, but how unique is that methodology might be?
The issue is that this test will work if your alphabet is, like you've said, your alphabet is size 2 and your sequence length is 1,000,000, or even in this case 100 or even 10, it would work. But if your alphabet is of size 500,000 and you're comparing like a normal document, which is much less than 500,000, then the run test will not
reject it.
Yeah. But this will work. So this is what you'll see is the example that we gave. That doing maximum likelihood, which I think is in some sense comparable to what you're saying, will actually fail on all these things that expect things to behave according to the probability. Because when you have a large distribution of few samples, you don't get things according to the probability that you expect.
Yeah, but the runs test is kind of elaborate because you don't... I'll have to think about it because it doesn't a priori assume what the probabilities are for you.
We also don't assume. Like like when we do maximum likelihood, we also do not assume. But we'll need to look at this test specifically, but I suspect that, like you said, for zeros and ones, it will work very well. Otherwise, runs will not give you that much information.
Yeah, the paper's 1940s is very worth reading for other reasons.
Sure.
Which I can tell you about.
Okay, yeah.
It'd be interesting to know why it's not good.
Yeah, okay, cool. We'll look. Thanks.
Quick question. So this is to understand which of these two numbers might be the right limit, 3.5, I think 3/2 or 7/6. So in the fitting of case, there is, you can get compression in a competitive fashion.
Right.
But there is some leeway, and that you have to give up something because of the complexity of the class. And that's measured by log n over n times some constant, which essentially tells you the degrees of freedom.
Right, that's right.
So is there a notion of complexity of IID class which might tell which of these two numbers is the right number?
There should be. We don't know. The fitting of case refers to alphabet which is finite,
yes,
and sequence line goes to infinity. Everything becomes a lot simpler, then things become logarithmic. Here we're looking at a case where the alphabet size, we don't even know what it is. And then things become more complicated, so we don't know. And then further complication is that here we're looking at pairs of sequences, not a single one. So if you ask the same question for compression for large alphabet, we do know the answer. But here we're extending it from compression to classification. It's a different kind of problem. There should be an answer, but we don't know. It becomes more complicated. And I can tell you that 1.5 is not the right answer. No.
We should move on to our final speaker.